Okay, thank you, Katya, and Knut for the invitation to give this talk. It's a pleasure to do this uh, seminar, although it's been quite some time since I gave a Zoom seminar, so I hope it goes well. So this is based on joint work with Katya and Gunther. Let's start with the premise of the talk, which is the so-called inverse problem with passive measurements. So I would like to begin with just at least in some sense philosophically say what it is that we want to study. And it's a particular type of inverse problem for evolution equations mostly, which is an inverse problem with a severely limited amount of data, where we ask whether or not it's possible to determine the structure of a medium, such as, for example, the geometry, wave speed, material properties inside the medium, using just a single measurement of the system's response to some unknown cause. Okay, so in this kind of inverse problem, we cannot make any inputs into the system. And also, additionally, to make the situation worse, we don't even know what caused the observations that we are seeing. We just see some observations where we can, in theory, put some equipment. So, for example, in a physical situation, you might consider in seismology the situation where you are on the surface of the Earth, and we can put some seismometers or radars on the surface at certain positions. And then let's say some earthquake happens at some place, we don't know where, with some unknown intensity. And now we have some observations. With this one observation, can we determine everything about the system? This is what we are after. And to follow up with this Q1, we should really ask under what kind of assumptions can we even hope to be able to solve such an inverse problem. And in this talk, my aim is to kind of give some kind of comprehensive results that solve these problems in a generic sense. And you can even, as we will see throughout this talk, see that these kind of generic assumptions are in some sense optimal. One cannot do better. Okay, so let's start with the mathematical formulation. And for this, I have to define the canonical Schrödinger operator, which conveys so much of mathematical physics. Okay, so for example, heat equations, wave equations, dynamical Schrödinger equation, which are the key equations in physics, are all based on this Schrödinger, static Schrödinger equation. So we start, and all of this talk will be on a bounded domain, okay, or a bounded manifold. The situation is a compact situation. So we start with a Riemannian manifold, which is compact, of dimension 2 or higher, with or without boundary. That's not really a big deal. And on this manifold, we assume that we have some real valued scalar function, which I refer to as the potential V. And then, of course, we have this canonical Laplace-Beltrami operator, which is a second-order self-adjoint differential operator, given in local coordinates by this expression. And then throughout this talk, I want to consider this Schrödinger operator on the Riemannian manifold as a sort of a object that is fundamental in studying a lot of physical problems and a lot of physics. And what is important to note, and this is basic theory of self-adjoint operators, is that for this operator, there exists an orthonormal basis in L2 consisting of eigenfunctions. Okay, so there exists a discrete set of eigenvalues, lambda k, that you can arrange in increasing order. And corresponding to these eigenvalues, you have an eigenfunction or eigenfunctions with some multiplicity. And the important thing is that they form, you can make them to form an orthonormal basis in L2. Okay, so this is the underlying object. And then to introduce again our inverse problem with passive measurement in the context of wave equation, it goes as follows. Again, this can be stated for your favorite evolution equation. If it is heat equation or dynamical Schrodinger equation, we can also do it. But I will just stick to the wave equation throughout this talk. Because this is related essentially specifically to an inverse problem in photoacoustic tomography as well. Okay, so the problem goes as follows. We consider the wave equation on a manifold or on a domain with boundary, let's say, doesn't matter. And we consider this wave equation subject to unknown coefficients. So we don't know the leading order coefficients, which appear here in the form of a metric. And we also don't know this zeroth order coefficient in the equation. Both are a priori unknown to us. And then this equation is solved subject to some unknown initial data. Okay, so the Dirichlet trace at time t equals 0 is given by f, and the Neumann trace at t equals 0 is 0. And then if the manifold has a boundary on the lateral side, so on the boundary, we impose 0 Dirichlet data. So the reason I have this model is that this is exactly the model for the photoacoustic problem, inverse photoacoustic problem with the so-called soft boundary, where this time derivative at t equals 0 is 0 there. So this is the only reason I'm putting this exact model throughout this talk. I should say that this time derivative being 0 is not important. You can even add a second unknown function h here, if you like. But because of its relevance to photoacoustic tomography, let me go with this model. And then what is the inverse problem? Well, we say, let's say we have some open set, non-empty open set in this manifold, where we can do our measurements. So going back to this physical example, let's say we have some equipments put on the boundary. So in this case, O, for example, actually would be an open set on the boundary, but you can imagine maybe we can even go a little bit inside the Earth and still do our measurements, okay? So then what is the inverse problem? Suppose that, well, there are two different metrics, potentials, and initial data. And suppose that the solutions corresponding to these two different systems are identical for all time that is positive in this region O that we are doing our measurements. And this set O a priori could be very small. Okay, so we are measuring the solution in this subset O. And then we are asking if this one measurement alone is sufficient to determine everything. Of course, the uniqueness has to come with respect to this natural gauge of changing coordinates, which I don't really want to go into the details of it. I will just write this congruence relation saying that basically they are identical up to the pullback of some diffeomorphism, okay? If the metrics are identical, then you really get equality. This is what you want to ask yourself. But if metrics are also unknown, then you can really, at best, hope to recover optimally up to this pullback of diffeomorphisms. Okay, so that's the inverse problem that we want to study. If two different systems with two different initial data give rise to the same measurement, must the two systems be identical? Let me say, while even in the case that the set O, just to gauge your attention a bit, even if the set O is the entire manifold, this is not an obvious problem. Even if you're measuring your solution everywhere, because the metric is there, it's not obvious. But let's say that case is not interesting and probably can be done easily, right? But just wanted to show you that even when you have measurements everywhere, it's difficult. But now imagine you are doing measurement in a tiny, tiny place and you want to recover everything everywhere. Okay, any questions up to now? Please feel free to unmute yourself and ask if something is unclear. If not, let me now go on with explaining why this is a spectral problem, really. And this really goes to this expansion, Fourier series expansion or eigenfunction expansion for any function. So we know that any function in L2 admits this kind of eigenfunction expansion, which I will also sometimes refer to as the Fourier expansion of the function f. And there is an isometry from f's in L2 to these coefficients in little L2. Okay, so basically, if you have some general unknown function f, these coefficients in this expansion can just be anything in little L2. Okay, so with this expansion of the initial data, you can write the spectral representation of the solution to the wave equation, which is given by this expression for u. Okay, so u also admits an expansion in eigenvalues and eigenfunctions, whereas you can see everything is unknown. The eigenvalues are unknown, the eigenfunctions are unknown, the function f is unknown. So everything is unknown. But what do we know? We know that the solution is measured on some subset O. So we know the solution on some subset O. So then maybe it's not hard for you to see that using some complex analysis and taking, let's say, Laplace transforms in time, probably one can get access to some kind of a spectral data, which is precisely some eigenvalues and these kind of expressions. Okay, so where basically we get basically all the terms in this kind of expansion where the j, lambda j is equal to lambda k. Okay, so if there is some multiplicity, it has a combining effect, right? A lot of these terms combine, and you can only recover this one expression corresponding to that one eigenvalue if there are multiplicities. Okay, so what can we get from knowing the solution on some subset O? We can get some eigenvalues, and we can get for each eigenvalue one kind of an eigenfunction restricted to the set O. Okay, because this expression in the end is also an eigenfunction, right? So it seems like corresponding to, let's say, each eigenspace, we can get, for each fixed eigenspace, we can get the eigenvalue for that eigenspace and one non-trivial eigenfunction. But the crucial observation is that this eigenfunction is no more an eigenfunction with L2 norm 1, right? Because it incorporates within it this initial data f that is also unknown. Okay, so we just end up with some kind of a non-trivial eigenfunction. That's it. On the other hand, if you can easily convince yourself that these problems are equivalent, the inverse problem with passive measurement that I've been discussing, and the problem of recovering everything from this kind of data. And that's because of this isometry from L2 to little L2. Okay. Now, what is known about this inverse problem? Well, actually, a lot has been done in this inverse problem in dimension 1. Because as you know, the inverse of spectral theory in dimension 1 is, in some sense, very well understood, even though there are still some open problems, but we have a very complete picture in 1D for inverse spectral problems. So in dimension 1, let's consider again this problem that I've been discussing. And let me introduce a definition, which is to say that I say an initial data and a potential is admissible if, first of all, the Dirichlet spectrum for the Schrödinger operator is simple, meaning that all the eigenvalues have multiplicity 1. And additionally, the initial data must generate all the coefficients. So there has to be a non-degeneracy assumption on the initial data, so that when you write its expansion in this sort of model, none of these terms are 0, because if they are 0, you lose completely access to that eigenspace. Okay, so the assumption that you impose in dimension 1 is that, first of all, all the eigenvalues are simple, they have multiplicity 1. And secondly, the initial data must exhibit all the coefficients when you write its eigenfunction expansion. Both of these conditions are generic in the sense of bare category. So for an countable intersection of dense open sets, these are satisfied. Okay, so this admissibility condition is a generic condition. You might tell me, well, obviously for a real valued potential, you do have simplicity of the spectrum. But remember, I mean, you can consider a complex valued potential, in which case then you lose this simplicity. And still you in 1D at least, if the imaginary part of the potential is a small, you have a complete spectral picture. Okay, so what is the theorem that is known in this case is that if you have an initial data and a potential that is admissible, so generic in the sense that I described above, then if you know, for example, two solutions are matching near the endpoints, let's say, or even at the endpoints, if you incorporate the normal derivative. But also, if you want to consider the setup that we have been interested in, let's imagine O is the neighborhood of the two endpoints. Then actually the potentials must be equal and the initial data must be equal. So you do have uniqueness within this generic family of unknowns F and B. Okay, the reason I haven't put a citation here is that in the context of wave equation, somehow this wasn't studied. But in the 70s and 80s, the parabolic exact inverse problem in 1D was studied. And these results are available under these generic assumptions. These results will also have appeared for 1D dynamical Schrodinger equation. And let me just say that this admissibility condition is sharp. So if you remove this admissibility, there are counterexamples. So you can have two different initial data and potentials that give rise to the same measurement. Okay, so the assumption is really optimal. Spectrally speaking, even if you lose one pair, an eigenfunction, an eigenvalue, you lose uniqueness. This is what it's all about. Okay, so if the set O is a neighborhood of the boundary, these were studied, we understand it optimally. Let's consider a different scenario where the region where we do measurement is not the two endpoints, but rather is a subinterval. So you can also imagine where we are doing our measurements in a subinterval around one endpoint. Then actually you even run into more problems. So even if you have admissible initial data and potential, in the sense that the initial data generates all coefficients and the potential is such that the eigenvalues are simple, even if you consider almost all the way up to half of the interval, you don't have uniqueness. This is a bit strange, but you can have a measurement set that is as large as almost half of the full interval, and still with a generic F1 and a generic V1, you still do not have uniqueness. So you need to have at least half of the interval. And then you might ask me, okay, what about the situation where there is no boundary, because this 0, 1 is an interval with boundary. So let's go to the unit circle in dimension 1. The problem becomes more difficult. And in this case, assuming that F and B are admissible again, so assuming that the potential is such that you don't have eigenvalues with multiplicity 2, because this can happen on a circle. So let's remove them by working with the admissible potential. Then still, the set O cannot just be any set. In particular, the set O must contain antipodal points. This is a result by Suzuki, where he says that if your observation set contains two antipodal points and you have a neighborhood of these, then you can recover everything under these generic assumptions. Okay, and by antipodal, I mean 2 points that are the farthest away. So of course, in the case of the circle with the usual topology, these are the usual, let's say, North Pole and South Pole. Okay, so in dimension 1, this problem is very well understood optimally. What about higher dimensions? And as far as I know, in this framework of a bounded setting, there are no results in the higher dimensional setting. There are some particular results with very strong assumptions if you go to unbounded domains, okay, under certain monotonicity assumptions and so on. But in the bounded case, we haven't been able to really see any results. So I want to now state some results that we have with Katia on this problem. And the first one I will state on a sort of a, let's say, a domain with boundary, because perhaps this is the easiest to understand. Okay, so I want to give the exact generalization of this, let's say, Suzuki results and all these prior results in 1D now in higher D. So the result goes as follows. Suppose you have a domain in Rn with a smooth boundary, and let's say that the set O is a neighborhood of the boundary. So you can just consider a tiny tubular neighborhood of the boundary where we can observe everything. Then assume that we have two unknown metrics on this manifold such that these manifolds are without conjugate points. Okay, so precisely what I mean, that there are no conjugate points along geodesics. Okay, and then of course in dimension 1 there is no such assumption because there is no geometry in a sense. So this is the geometric assumption that we impose on the metric, on the leading order coefficients. There is this natural assumption that I hope I have conveyed, that there is no escaping from, the genericity assumption. So I'm going to assume that the potential and the initial data belong to a generic set. And you know precisely what I mean. What I mean is that the operator minus Laplace plus potential must have a simpler spectrum. The eigenvalues should have multiplicity 1, and the initial data f must exhibit all the coefficients. As I said, this is a generic condition. So it's satisfied for a very large set of data, topologically speaking. Now, within this generic class, suppose we have two different metrics and two different potentials and two different initial datas, and then we solve the wave equation for each of these. Suppose that our measurements for these two systems turn out to be the same in this tiny tubular neighborhood around the boundary of the domain. Then everything is equal up to the natural gauge, okay, of diffeomorphism. Okay, so the metrics, potential, and the initial data are equal to each other up to the pullback of some diffeomorphism. And so we can solve the problem completely under this genericity assumption for bounded domains. Assuming, of course, you have general metrics. What about, so now I want to address the second theorem, which we also discussed, for example, some cases without boundary. And I will only state some examples because I want it to be understandable. In the paper, we do it more abstractly. But this second theorem now, I want to give it a rigidity flavor, okay? Because in the first theorem, let me make this remark that some might say that, okay, this is a generic uniqueness result in the sense that you are saying, let's stick to this data set, which is generic. And as I said, in the 1D case, I mean, in some sense, this is the best we can do, right? But we can actually go one step better by just imposing this genericity assumption on one operator and a priori making no assumptions on the other operator. Okay, in this, by doing so, we can really obtain truly uniqueness results in the sense that we now want to ask, suppose our data, what we measure, seems to be arising from some kind of a generic system, then is that system unique within the class of all possible systems, all possible potentials, metrics, and initial data? Okay, so with Katia, we can also have this large class of rigidity results, but only for lower order coefficients, not for metrics. Okay, so just to give you some flavor of these kind of results, let me give you three kind of geometric examples. So in the first one, let's say that I have a manifold which is simple, with boundary, and O is a neighborhood of the boundary, much like the previous case. Suppose alternatively that I have a manifold which is just the n-dimensional flat torus, and O is a neighborhood of the center and the corners. It doesn't even have to be connected. So it's a neighborhood of the center and the corners of this torus. Or alternatively, let's just consider a closed manifold, a manifold without boundary, and imagine that the complement of this region where we are doing our observations is simple, meaning that the geodesic flow doesn't have conjugate points and its boundary is strictly convex. Then suppose that I have suppose I have initial data F1 and a potential V1 that is generic in the sense that the spectrum is simple and the initial data F1 generates all the coefficients. But you notice that I only impose this genericity on F1 and V1, nothing on F2 and V2. Then assuming that the two solutions match on some part of the observation set, we can conclude that the two potentials must be equal to each other and the two initial data must be equal to each other, without even assuming anything about V2 or F2. So in this sense, now we can also, for recovery of lower order coefficients, get a large class of rigidity results for this kind of inverse problems with passive measurements. Okay, so what is really at the basis of getting these results for these inverse problems with passive measurements? And the key is a new kind of inverse spectral problem that we study with Katya and also with Gunther. And this is a kind of inverse spectral problem that, formally speaking, I will introduce it in this slide, and it goes as follows. Okay, so suppose we have two Schrödinger operators, minus Laplace plus potential, and I always refer to these two systems with a subscript index j, which goes from 1 to 2. Okay, so we have these two Schrödinger operators on a priori, let's say even two different manifolds, even topologically speaking. So let's say we don't even know the manifold, we don't know the metric, we don't know the potential. But what we do know is that there is some subset, a linearly independent subset of eigenfunctions, such that these eigenfunctions are equal on the set O. Okay, so let me explain again what I mean. Suppose that, so there is this identity here, this identity 5, that is at the cornerstone of this inverse spectral problem. And it takes a little bit of time to understand what is being asked here. So what is being said, because you see there is a equality of eigenvalues and eigenfunctions, but the indices don't match and they are somehow completely arbitrary. So let me just give you a bit of intuition what this means. It kind of means that suppose that we know that the spectrum of the first operator, and not even the full spectrum, but part of the spectrum of the first operator is a subset of the spectrum of the second operator. Okay, so we don't exactly know the ordering of the eigenvalues, but what we are asking is that the eigenvalues of the first operator, for example, some of them are equal to some other eigenvalue of the second operator. And then we have this kind of equality of corresponding eigenfunctions, but the eigenfunctions are not orthonormal. And I cannot emphasize this enough. The eigenfunctions are not orthonormal and they are only assumed to be linearly independent. This is an important assumption because going back to this framework of inverse problem passive measurements, these eigenfunctions are somehow related to the initial data that is unknown. Okay, so we can never normalize them. Okay, and then from this kind of equality of some eigenvalues being equal and some eigenfunctions being equal on the set O, can we recover everything, the metric and the potential? This is a new inverse spectral problem. It's new because you don't have the full spectrum, you only have some of the spectrum. The indices here are not matching, and by Weil law, actually, they can mismatch up to a very large amount. And then the eigenfunctions are not even orthonormal, so no norming constants are known about them. All you know is that some eigenfunction of the first operator is equal to some eigenfunction of the second operator. Okay, so this inverse spectral problem actually has been studied in dimension 1. let me just quickly give a review of it. So in dimension one, again, we formulate this kind of eigenvalue problem. Let's say the Dirichlet eigenvalue problem, where these eigenfunctions must be zero at the two endpoints. And then we pose the inverse problem that I posed in the previous slide, okay? So for each eigenvalue, of course, we know that in the case of a real valued potential, there is one multiplicity. So then we are saying, of course, the eigenspace for each eigenvalue has dimension one, right? So if you know one eigenfunction, then any multiple of that would also be an eigenfunction, right? But that constant somehow is lost for us because that constant somehow is related to norming constants. So all we are asking is that suppose some kind of eigenvalues are equal with some indices, and then one of the eigenfunctions in this kind of eigenspace of dimension one is equal to one of the eigenfunctions in the other space, okay? Can we show that the two potentials are identical? So first of all, let me say something. In dimension one, these indices don't cause you a lot of problem, the mismatching of the indices, because the while law in dimension one is truly special. What do I mean by this? Well, you know the eigenvalue asymptotics in dimension one up to arbitrary order. So by writing the eigenvalue asymptotics, you can see that for k large enough, actually the indices should be equal. So this mismatch of the indices in dimension one is not a big deal. In dimensions two and higher, it's a big deal. Okay, so what is known in dimension one? Actually, this goes back to the seminal work of Borg and Levinson, that if you know all the indices, so if all the AKs and BKs are K, and if O is, let's say, both the endpoints or near the endpoints, then you can solve the problem. Even though you don't know norming constants, it's not a big deal. The fact that you know them near both endpoints, you can still recover the potential. But that's a special case where O is a neighborhood of both endpoints. What if O is a subset, let's say, from one endpoint? Then actually it becomes a bit funny, because if this set O is from 0 to something less than a half, you don't have uniqueness for this inverse spectral problem. You cannot have it. There is a lot of potentials with the same kind of spectral data, even if you know all the indices, even if AK and BK is K for all K. Hofstad and Lieberman say that you need at least half of the interval, and this is optimal. And then Geshtezi and Simon say that if you go beyond one half, then you can even go to a subset, AK. Like you don't need the full spectrum. You can get rid of, let's say, if you go epsilon beyond one half, then you can get rid of 2 epsilon fraction of the spectrum entirely and still recover the potential uniquely. And Horvath has some results which essentially show that this kind of this is done in an optimal way. Okay, so it really characterizes this link between this kind of data and the reconstruction of potential in an optimal sense. Okay, all of these results are entirely based on complex analysis, as you would expect, and interpolation properties of holomorphic functions. It's quite a beautiful subject, but it's something that you would never hope to generalize to higher dimensions. For one thing, in 1D, eigenfunctions are solved from one endpoint, you know, a Cauchy problem. In higher D, you don't have this. Anyways, all of these results are entirely based on complex analysis. Okay, so we would like to obtain similar results in higher D. Let me say, okay, I cannot discuss this problem without saying something that has been studied in higher dimension related to these inverse spectral problems. This is the multidimensional Borg-Levinson and also Gelfand inverse spectral problem, but it's a different problem to what I've introduced. Essentially, the Gelfand problem says that suppose that you know the equality of all the eigenvalues and the indices are matching. But even more importantly, okay, maybe I shouldn't say more importantly, but this is really fundamental, is that the eigenfunctions are orthonormal. Okay, so you know that you get the equality of eigenfunctions corresponding to an orthonormal basis, meaning that all of these are such that globally the L2 norm is 1, and yet you know that for these normalized eigenfunctions, you have equality on the set O. Then do we get that the potentials and the metric are isometric? And actually, this problem has been solved in full generality. The answer is affirmative. The most complete result on this was by Belishev and Kurilev in 92, where they did it on a manifold with boundary, and assuming that O is, let's say, on the boundary, and you are recording the normal derivative on the boundary. But even if you have a manifold without boundary and O is an arbitrary open set inside of it, this can be done. This proof of Belishev-Kurilev indeed was extended to such settings by Katya, Slava Kurilev, and Mati Lasas. And I refer you to this book of Kachalov, Kurilev, and Lasas for an overview of such results. Let me also say that if the metric is known and it is only the potential that you want to recover, there is an alternative perspective of this approach to these inverse problems, because this kind of Belishev-Kurilev results and the results that followed use the boundary control method. If the metric is known and you want to just recover lower order coefficients, there is an alternative approach based on geometric optics and complex geometric optics that I've listed some references here. But in all of these results, it's important, first of all, that you know the eigenvalues are coming from the same index. So more or less, you know all the spectral data, or at most, maybe you lose a finite number of eigenvalues. And then you have equality of eigenfunctions corresponding to some orthonormal basis. Okay, so in our case, actually, these results do not apply because the eigenfunctions are not orthonormal, and the indices here are also, in our case, could be a priori mismatching. Okay, so let me now, I said this maybe 10, 20 times, but let me at least try to say why the orthonormality of eigenfunctions matters. The reason it matters, again, somehow has to go conceptually to the eigenfunction expansion of a function. So suppose so remember, in all of these problems, there is somehow an open set O where a priori, this is referred to as the observation set. It's supposed to be a set where we can do measurements, right? So this is the set. Maybe it is very small, but nevertheless, we can do measurements in this set O. So now imagine I give you a function f that is supported in this set O. Then by spectral theory, you know that if I have a basis of eigenfunctions, then I can write the function in terms of that basis with some coordinates. And this the concept of a basis is referred to as a Schauder basis. So let's say we have a Schauder basis of eigenfunctions. Then, okay, I have a function. In theory, I can write it with some coefficients. The function is known because the function is living in this kind of in this subset O where I'm doing our measurements, right? So a priori, I can just use any function that I like. The eigenfunctions in this set O are known. Again, let me remind you, I know eigenfunctions in the set O. Now I ask a simple question. Can you tell me what are the coefficients? And then you will say, no, I don't know the coefficients, because the coefficients, figuring out the coefficients is a global problem, unless the eigenfunctions are orthonormal. If the eigenfunctions are orthonormal, then actually all these coefficients are constructed via this local problem of integrating f against the restriction of the eigenfunctions on the set O. And if I lose this orthonormality of eigenfunctions, I lose this knowledge of how I write a function in terms of eigenfunctions. I lose all these coefficients entirely. So conceptually, this is somehow why, methodologically speaking, this orthonormality is important. Now, let me say why orthonormality is important. Also, no. Okay, so Right. So let me also say another reason why they're important, and this is more or less by using the 1D perspective and giving you counter examples, right? That says that, okay, for this kind of a spectral problem, if you take non-orthonormal eigenfunctions, and if you just take a set O that is not the correct set O, you can even lose uniqueness for this inverse spectral problem. And I will give you one example where the set O is in fact even very large. Okay, so what's the example? Let's take the unit circle S1 cross an interval 0, 1. Okay, so this is a, let's say, a smooth, cylinder. So it's a two, so I'm talking about a manifold, which is the surface of this cylinder. Then actually, surprisingly, but maybe you're not surprised too much because this is a product topology and I'm invoking this 1D results. There actually exist two different potentials on this cylinder such that all of the eigenvalues are equal, and there exist some non-orthonormal eigenfunctions which are equal on the set O, where actually this set O is almost half of the cylinder. It goes from one endpoint all the way up to almost half of the cylinder. Even if your set O is this large, and even if you know the full spectrum, because these eigenfunctions are non-orthonormal, you lose uniqueness for this inverse spectral problem. So maybe now, hopefully I've convinced you why this matters. Okay, so we have results on this problem. The first result is for the recovery of topology and the metric in general. This is a result with Katya and Gunther. It goes back to last year, early last year. And it was a result that we discovered when we were working on a completely different problem related to fractional type of anisotropic inverse problems. And this is an ingredient that there we needed. And it was surprising actually to us back then that we could get this result. So to state this result, let me first define the antipodal set, giving you a reminder to 1D results where the context was clear. So suppose I have a compact manifold now, with or without boundary. What is the antipodal set of a point? It's the set of all points Q in the manifold, which are the farthest from the point P. Because we are in a compact setting, the antipodal set of a point always exists. It's a compact set. It's non-empty, but I mean, it could be very complicated. And these antipodal sets have been studied and they are interesting in their own right. But for example, if you take the two sphere, for example, the antipodal set of a point is the corresponding natural point that is sitting at the opposite end, right? South pole and north pole. Okay, so what is the inverse spectral result that we have with Katya and Gunther? It goes as follows. Suppose we have two different Riemannian manifolds, a priori on two different manifolds, topologically speaking. But let's say we have some common observation set. So an open non-empty subset that is sitting inside both of these manifolds. And then the assumption that we impose is that when you look at the manifold minus this observation set, so when you look at the complement of this manifold, the complement of this observation set, so this is the region that is somehow the unknown region. This is the region where we don't know anything about. We need to assume some conditions on it. Namely, we are going to assume that the complement of this set is non-trapping. All the geodesics must exit it in finite time. And secondly, is that there is a point P in this observation set such that its antipodal set is also in the set. Okay, so let me give you some example that makes this understandable. For example, let's imagine that I have a domain in Rn, a bounded domain. Then, for example, this condition is always satisfied if you pick O to be a neighborhood of the boundary. And then this condition just means that the manifold, this domain has to be non-trapping. Every geodesic in the domain must eventually exit it. Okay, just to give you an example of what this geometric assumption, for example, means in a situation of a bounded domain with boundary. Then we can solve the inverse spectral problem that I posed assuming that you have the full spectral data, but the eigenfunctions are not orthonormal. Okay, if you have such an equality for all indices, then the two manifolds must be isometric to each other. Okay, so we actually are able to deal with the fact that the eigenfunctions are not orthonormal in this work. But of course, in this work, we need to know that we have access to all the eigenvalues. For recovery of metric and geometry, this is still the best result that we have. We cannot do any better. Okay. But the story is that with Katia, we have noticed that when we go to lower order coefficients, we can even start to lose parts of the spectral data also. Okay, so I want to now state that result for recovery of lower order coefficients. And here we have two kinds of results. In the first result, we consider the same problem, okay, with the same geometrical setup as in the previous slide, but now the unknown is a potential, okay? So now I assume that I know the manifold and I know the metric, but there is an underlying potential that is unknown. And then I pose my inverse spectral problem, okay? But now I say that, okay, first of all, the eigenfunctions are not orthonormal. But secondly, you see, now I say that imagine that, okay, first of all, potentially a finite number of eigenvalues of the first operator are missing because you see the index only starts from some capital N. And secondly, a priori, I don't know anything about the matching of the indices. All I know is that the spectrum of the first operator after some point is a subset of the spectrum of the second operator without imposing any assumption on these indices of the second operator. Then can you solve this inverse spectral problem and recover the potential everywhere uniquely? And the answer is yes, we can do that. So that's the second result. And then the third result that we have goes one step even beyond this by saying that, okay, let's now try to lose an infinite number of eigenvalues of even the first operator, which in some sense is a bit of an uncharted territory. The only other result that I know of this is in the 1D case, Gechte Simon. But now we want to go to higher D and lose also an infinite part of the spectrum of the first operator. So here, of course, I have to define how much of the spectrum of the first operator I can get rid of. It's a bit of a technical definition, but let me just say that rather than going through this technicality, because I'm running out of time, let me say, for example, generally speaking, to make it simple to understand, you can always drop a logarithmic fraction of the spectrum of the first operator, in the sense that from the first k eigenvalues, drop log k of them. Okay? So this is somehow to quantify how much of the eigenvalues of the first operator you can entirely miss from your spectral data. Okay? And then in this setting, because now we are going in this direction that we are losing a lot of the spectrum also from both operators, we need to impose some kind of a uniform observability estimate also on eigenfunctions that is stated here, which says that we need an estimate that says that globally speaking, the L2 norm of any eigenfunction can be uniformly bounded by the L2 norm of that eigenfunction on a subset of any subset of O. Okay, where the constant can depend on the subset, but not on the frequency. Okay, these observability estimates actually generally cannot obviously be true because unique continuation is very much ill-posed and you don't have these constants that do not depend on the frequency. But there are certain examples where these are true. For example, for the flat torus, these kind of observability estimates are true for any eigenfunctions independent of the frequency. For anosoph Riemannian surfaces, they are true, or more, for example, for Riemannian surfaces of negative curvature, these are true. And it is even a big conjecture that these kind of estimates are true for Riemannian manifolds of negative curvature in any dimension. But this is a widely open problem. Okay, so then the third inverse spectral result that we have with Katia essentially is in the same setup as I've been discussing. We want to recover a lower order coefficient again. But now I go into this framework where now we are going to lose a lot of the spectrum. So first of all, let's say lose a logarithmic proportion of the first spectrum entirely, and then say that what is left is only a subset of the second spectrum. And then we have the corresponding equality of the eigenfunctions on the set O. Then actually you can recover the two potentials uniquely on the manifold everywhere. Now, yeah, I was naive enough to think that I will get time to go over some bit of proof, but I think, yeah, I won't have time for that. So, Katya, how much time do I have, by the way?
You can take some more minutes, 5 minutes.
Okay, if I have 5 minutes, maybe actually I can discuss at least this proof that we have with Gunther in the case where all the indices are present. So you have the full spectrum, but the eigenfunctions are not orthonormal. And the unknown is the metric and the manifold. Okay, so let me go over that quickly. So this is the setup again. So I have the equality of all the eigenvalues, and I have the equality of some eigenfunction corresponding to each eigenvalue, but they are not orthonormal. Okay, so what is the key idea here? Okay, and by the way, so the unknowns are, for example, this minus Laplace plus potential, right? And let's say we know the manifold, at least let's, for the simplicity of the presentation, let's say the manifold we know topologically. So then remember the assumption that we had with Gunther and Katia was that the complement of this observation set should be non-trapping, and there should be a point in this set O such that the farthest points that are from this set O are again in the set O. It's a bit of a strange assumption, but actually it's a neat assumption because a priori this set O can be very small. For example, if you have a manifold with boundary, you can just take this set O to be a tiny neighborhood of the boundary. Okay, so what is the general strategy in this case? The general strategy is that actually from this kind of equality, we can get access to the equality of all the norming constants. We can get to the equality of the normalized eigenfunctions, the one which are orthonormal. How do we do this? Well, firstly, as I said, we need this kind of observability estimates for eigenfunctions. We need some kind of estimate for eigenfunctions independent of the index that says that globally their L2 norm on the entire manifold can be bounded by knowing their L2 norm on a subset of the on the set O, independent of the frequency K. Okay, so for example, the non-trapping assumption that we impose guarantees that this estimate is true. This goes back to the work of Roche and Taylor in 74, I think, for, if I remember correctly, for the case of manifolds without boundary, and for Bardouche, Lebo, and Roche for the case of manifolds with boundary, because there's a whole essentially bag of worms that get opened up when you're working with manifolds with boundary. Okay, so this is where this non-trapping assumption for us comes in this theorem that we had with Gunther and Katja to get this kind of estimate. Okay, so the setup again, if you like to think about a bounded case with a case of a domain with boundary, your set O is looking like this gray set, a neighborhood of the boundary. Then our strategy is the following. Let's take a point. I will not discuss the torus case, but here I'm just saying that, okay, for the torus, what things look like. So in the case of a domain with boundary, I just pick a point P, let's say on the boundary, and then I go to a point Q that is the farthest from P with respect to this metric G. So that, assuming we are Euclidean here, that to me kind of looks like this point Q. That is the point that is the farthest from this point P. Okay, so what is now our strategy? Our strategy is to now work with functions that are supported very near this point Q and see what we can do. Okay, so if I have a function that is supported in an epsilon neighborhood of this point Q, then of course that function admits this kind of expansion with respect to the first basis. And then I'm going to do something a bit funny here. I'm going to take the coefficients that I get from, because this is a Schauder basis, right? So I get some coefficients here. And then I'm going to take these coefficients and I stick it in front of the second basis and form a new object, which I call F2. Now, you have to be extremely careful because a priori this function F2 may not even be well defined. So we need to make sure that all these objects are well defined, and the non-trapping assumption guarantees that all of these are well defined, okay? But I will not describe this in detail. So we form this second function that somehow has these coefficients again, but now I don't know what this function is because it's a global function, right? What I want to show for the rest of the proof is that this function f2 actually is equal to the function f1. And the way I do it is by forming this solution to the wave equation corresponding to this index j. Okay, so these functions, capital Uj, solve these kind of wave equations. It's easy to see. And furthermore, these solutions, in particular, the first solution seems to be coming from genuinely some initial data f1. The second one is coming from some initial data f2 that I know nothing about a priori. But the first solution to the wave equation is coming from something that is supported near Q. So looking at what Q is, the solution to that wave equation will remain zero for a very large time until the signals reach P. Okay, so for a very large amount of time, precisely this amount of time, the solution for the first wave equation is zero. But then, this means by the equality of the eigenfunctions on the set O and the equality of eigenvalues on the set O and equality of these coefficients, because I just chose them like that, means that capital U1 is equal to capital U2 on the set O, which means that this U2 also will remain zero near P for a very large time, precisely this amount of time. But here now I invoke this sharp unique continuation result of Tataru that says that, okay, if you know that this solution is vanishing for this amount of time, somehow I can go back and say that there is this region in a space at time t equals zero where the solution must be zero, precisely this region. And now, because I know that the initial data for this second wave equation is zero for a very large amount of time, precisely this amount of time, and because of the structure of the open set O, now I kind of fall back again into the set O. And this tells me that the two initial data actually must be globally equal to each other, meaning that this equality that I wrote in the previous page actually converges to the function f. What this means is that if you take any function near the point Q, the coefficients that you get for their eigenfunction expansions are identical. And from here, we can show, with some linear algebra that we can go to orthonormal eigenfunctions. Sorry if this was a bit rushed, this last 2-3 slides, but essentially, yeah, this is what I wanted to discuss about the proof. So I think, yeah, this is a good place to stop. Thank you very much for your attention.
Thank you very much, Ali, for the very nice talk. Thank you so much. Are there any questions or comments, please? Any questions or comments, please?
Hi, Ali. Can you hear me?
Hi, Temo.
Thank you for the
fantastic.
Thank you for the fantastic talk. It was very nice. So in this last proof that you just told us about, so was now the reason that you need to take Q as far from P as possible, that you can really somehow cover this whole set U with this kind of domain of dependencies which come there? Because of course now for the argument, which seems like, okay, so Q could be anywhere there in the domain, but now then maybe the domain of influence would not cover the whole O or something.
Yeah, exactly. So there is two things that come here quite amazingly that help each other. So first of all, because this Q is far away from P, you know that for the very long time, you're not going to see anything at Q by domain of dependence, right? Of course, this is, I mean, Q can be anywhere and up to a certain time covered by domain of dependence, you will not see anything at Q. But the reason that I picked it to be far away, the farthest away, is the second part of the proof that says that, okay, for a domain of dependence amount of time, of course, you don't see anything at Q. But then by Tataru, you can reverse this process and say that because we are not seeing anything here, then for a certain amount of time, we also don't see anything at the initial time. But somehow we want this certain amount of distance from Q to cover everything again so that we go back to this region near P. So unless this point Q is exactly somehow near the point that is farthest away, you can never really cover everything by this domain of dependence and Tataru. There is always some region that will be missing. Right? So this is why this antipodality for us is key, even if you have the full spectrum. But what is amazing is that even in 1D, this antipodality appears for complex analysis reasons. So maybe there is something deeper going on. There it's completely related to complex analysis.
Yeah, thank you. That was, I really enjoyed like how you explain like how you need both of the assumptions, the non-trapping which comes from the control theory, and then this antipodality which comes from this proof. Thank you so much.
Thank you so much, Temo.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Okay, if not, thank you very much, Ali, for the very nice talk. Thank you very much. Thank you very much,
Thank you.
everyone, for coming.